what I'll do is the problem session, because we didn't have a clear picture of what to do with the problem session. So as Professor Moffat said, we assumed a little background in topological graph theory, and with what the lecture which Professor Moffat has given, we want you to develop the concepts. It was a matter of developing the concepts just for you to have a feel of the topological graph theory. Then after that, what we are going to do is I will give you some problems which one can do just to develop the concepts. Once you develop the concepts, then we can look at well-established problems which people have already done. Then after that, we are going to introduce a new accessible open problems. So it will just take you, the first part will just be for you to make sure that you develop naturally develop the concepts. And after that, then we can show, just showing you what type of problems people solve in this field. And after that, then we can introduce just a few open problems which are accessible with the concepts which we have introduced, which we have introduced today. So I will just record the concepts which Prof. Moffat introduced. When we have a ribbon graph, we have a few parameters. VG, it will denote the number of vertices of a graph G, and we're talking about a ribbon graph here. EG, the number of edges. FG, the number of boundary components of our ribbon graph. KG, number of connected components. And gamma of G, which is the Euler genus. And this one, as Prof. Moffat said, it is just the genus if it is non-orientable, and twice its genus if it is orientable. And I'm also going to recall Euler's formula, which we introduced already, that you have the number of vertices minus the number of edges plus the number of boundary components equals 2 times the number of connected components of our graph minus the Euler genus. So let us look at this graph G, which a ribbon graph G, which we are given here. These are the edges. We have the ribbons 1, 2, 3, 4, 5, and 6. So just for you to have a feel, and with the concepts which were introduced, I think logically it would be interesting for you to try to compute the genus of this graph. Can you try to compute the genus of this graph? Then from there, we are going to do other things. I'm not going to solve the problems. We are not going to solve the problems now because Prof. Moffat gave already some examples how to do this. But we are just giving you a feel that this is a way like a direction how you can go about it, so that you have a good feel of the field or the topic. You start computing the genus, play around with the graph. How can I find the genus of this graph? Then once you understand the concept of the genus, then we go to the graph operations, which Prof. Moffat already introduced. G minus A, it is the subgraph which you obtained by deleting all the edges in A. And we had G contract A. He showed you how it is complicated to do the contraction of the graph. And we had the partial dual of G with respect to A, and we have the geometric dual G star. So with these concepts, you know the genus. Now we would want you to just a question for you to develop a field of this contraction, deletion, finding the partial dual, because all these concepts you need for you to understand the actual open problems, you need to develop this. So you should be able to try and solve certain problems, try to find these subgraphs on your own. So I've taken the same graph which I introduced. So with this graph, can you compute the following? One, can you find the ribbon graph G contract E, which we call a minor? Can you find this minor or this subgraph G delete E? Then after that, if you are able to do that, can you find the partial dual with respect to E, to an edge? And this edge is equal to 1. This one, we are looking at this loop. Can you delete this one and just find what the subgraph is? After that, can you find the partial dual? We are just using this edge 1. Find the partial dual, then contract it and see what happens when you contract this edge. Once you've done that, you can also try, just to be sure, try to find the partial dual. The partial dual of G with respect to A, where A is the edge set 3, 4, 5, 3, 4, 5, and try to find the partial dual of that. You can also try to be adventurous and try maybe to find G, delete A, G, contract A. You can do anything there. And also when A is equal to 1, 2, 6, 1, 2, 6, try to find the partial dual. So, and this will just help you to develop the concepts which have been introduced today. And so once you have done that, we want you to be able to draw some of these graphs. Let's say you have an edge E in your ribbon graph. These are edges. It can be a loop and an unloop, your edge. It can be an orientable loop or an oriented loop. You can have all these types of edges. You can have 3 types of edges: an unloop, an orientable loop, and an oriented loop. So for each of it, can you try to draw how G, the graph G, the ribbon graph G, or the graph G with the partial dual of G with respect to E and G contract E? Can you draw the 3 graphs and see how they differ locally at the edge E? Can you try to draw that? So this is just a practicing, just playing around with the concepts which we've introduced, and for you to see what it means to contract, finding the partial dual, and also what does it mean to have an unloop or an orientable loop, etc. So if you are able to do that, you are developing the concepts. So I'll recall again Euler's formula, because we are still, most of the problems which we are going to introduce, we are going to use Euler's formula. So I recall we have already talked about it, but can you use Euler's formula now that you are able to draw the graphs? You are able to find the Euler's genus. Can you use the formula to show that the Euler genus of the graph G, of your ribbon graph G, it is equal to the Euler genus of the dual of the, it is equal to the Euler genus of the dual of G. So this is one of the problems which we are just showing that, okay, there are things which you can do with ribbon graphs. There are problems which one can solve, And these are already done. They are easy, which people have done. Can you, and this part 2, you have the Euler genus of G is equal to the Euler genus of G delete E plus I, and it is equal to the Euler genus of G contract E plus J, and it is equal to the Euler genus of the partial dual of G with respect to E plus K. So for what possible values of I, J, K, for you to have I, J, K, for all these to be equal to the Euler genus of G. So here, the job is to find these values, I, J, K. Can you find the values of I, J, K, which can give you all these 3 equations? So this is how you can play around with the concepts which we have introduced. And you build on from there. We introduce the Euler characteristic, which is just the number of vertices minus the H set plus the number of boundary components. That is the Euler characteristic. So question number 3 is going to talk about the Euler characteristic. For a subset A of edges of a ribbon graph G, we are going to let G, this one, G restrict A, be a ribbon graph obtained by G to the edges of A. So this one, it is just representing that we are restricting G to the edges of A. We are taking A as it is in G, but we are just restricting it only to A. And here we have G restricted to the complement of A. So this symbol here, it is restricting. Once we have this, the question is, can you prove that the Euler genus, can you prove that the Euler characteristic of, and this one, it is the partial dual of with respect to A. Can you prove that the characteristic of the partial dual of G with respect to A, it is equal to the characteristic, the Euler characteristic of G when restricted to A plus the Euler characteristic of G restricted to the complement of A minus 2n. And this 2n, it is the number of vertices which the restriction of G to A and the restriction of G to the complement of A have in common. The number of vertices which these 2 graphs have in common, that's the n. So this is one of the theorems which one can prove. And you can see this, Professor Moffat proved this, and you can find it in this paper, which is in the European Journal of Combinatorics. And the title of the paper is Separability and the Genus of the Partial Dual. You can find this result in there. So you can see that here, the concepts which we've done, which Professor Moffat has introduced, you can build from there and start solving problems. You can start solving problems that fast. And I will introduce question number 4. And this question number 4, it is the one which is going to, I think, it is going to take us, I think, to the end. We'll talk about this. The partial dual, we are introducing now a polynomial. These polynomials were introduced by Gross, Mansfield, and Tucker. And you can find here on the footnote, you can find the name of the article which it was published in. So they introduced a polynomial which we call partial dual Euler genus polynomial. And this one, you can see it is denoted by this, and it is just the summation. You sum over all the subsets of the edge set of your ribbon graph G. And this is, you have Z here, and you have this, which is the Euler genus of the G, and with respect, the duality, sorry, the partial dual of G with respect to A. So you need to, you can see that you need to know how to find the partial dual, the partial dual of G with respect to A. You need to find, to be able to find the Euler genus. Then after that, the subsets, getting the subsets is not complicated. So this is why we started introducing with the problems of you finding the Euler genus, once you've, and also how to find to draw the partial, to compute the partial dual of G with respect to A, because you will need this. So for each subset which you have A of the H set, you are going to find the partial dual of that subset. And once you find that partial dual, you are going to compute the Euler genus of that partial dual. Then you take Z to the power, that one, the way the partial dual, and you sum for each subset, you do that and you do the sum. And this polynomial, we are going to call it the partial dual Euler genus polynomial. And there are two polynomials. And once you have done that, there is a second polynomial. When G is orientable, and orientable surfaces, orientable graph, which Prof. Moffat introduced. When it is orientable, then we can introduce the partial dual orientable genus polynomial. And this genus partial dual orientable genus polynomial, it is also defined as a sum over all the subsets of the H set. And here, the difference with the Euler genus is that here now you are just raising it to the power genus over the partial dual. So here you are raising it over the Euler genus, and here you are just raising it over the genus. And these two polynomials they are not very odd. As you see, the paper here, when they were introduced, it is just last year, 2020, it was published in 2020. So the concepts are still fresh and new. You won't find a lot of papers in it, but there is a lot of work which one can do, and also which other people are doing. So once we introduce this, can you compute? Now the question is, can you compute the partial dual Euler genus polynomial and the partial dual orientable genus polynomial for all ribbon graphs on up to 2 edges? The reason why we are putting this question is that for you to get used to the computation, because you can see we are saying up to 2 edges. You have seen that if I take you back, we are taking all the subsets here of the edge set. So if you have 3, let's say if you have three edges, you have a lot of subsets. We are saying, okay, just try with the 2 subsets so that you don't have a lot of subsets which you are summing. So it is doable. Once you are confident that you can do it, then you can increase the number of edges. You take ribbon graphs maybe with 3 edges, etc. But you should know that here the computation, you know how many, when you have the subsets, when you take the subsets, it will go to bigger numbers. Once you have many edges, the number of subsets will grow. And but yeah, once you are able to find the partial dual, then this is something which is already done. Can you prove that the partial dual orientable genus polynomial is interpolating? By interpolating, let's say it is of this form. You have a, k, z to the k, up to z plus kg here. So where from OAK up to AK plus AJ are non-zero. And sometimes you just say that the polynomials has no gaps. So can you prove that the partial dual orientable genus polynomial is interpolating, i.e. you can find that it is equal to AK up to Z to the K up to the, where the AJs, AKs are non-zero. So you can see that from all those concepts, we are building up to a lot of, you can build up to a lot of questions, problems which one can solve. And question number 7, which one can do, is by considering this graph, which I've given here. Can you show that in general, the partial dual orientable genus polynomial is not interpolating? So the first one, the previous question, we were proving that the partial dual genus polynomial is interpolating. But for this graph, you can see for this graph, show that in general, the partial dual orientable genus polynomial is not interpolating. In general, it is not interpolating. And this result, you can see it. It is in the footnote, which is here. Counter examples to conjectures. The conjectures which Grossman, Stew, and Tuck are the ones who introduced about the partial dual orientable genus polynomial and the other polynomial. They had conjectures, and you can find their conjectures in their paper. But this is an example which Jan and Jean gave to just a counter example to the conjecture. And you can find it in this paper. And so there are a lot of things which you can build up to, which you can do with the polynomials. And here, another question, which is interesting, which is already done. We have the footnote. Consider a family of orientable ribbon graphs defined through these pictures. And these pictures here, you have for B1, where here, this red circle, it is the vertex, and the blue line, it is just indicating where the edges should go. So you have this circle, and this edge goes from there to there, and go there to there. So this is B1, B2, up to B5. Don't forget that these are ribbon graphs. This is just a simplification of it so that we don't draw complicated diagrams in 3D. So once you have B1, B2, up to B, let's say Bn, in this family, can you prove that? Can you prove that when n is odd, the partial dual orientable genus polynomial is constant? Can you prove that when n is odd, the partial dual orientable genus polynomial is constant? In fact, these are essentially the only ribbon graphs with a constant partial dual orientable or Euler genus polynomial. These ones, the B and BI, they are the only graphs which have got these polynomials are just a constant. And you can see in the footnote that you can find this result from the paper of Chimtov and Fignes on a conjecture of gross Matthew-Tucker which is already, and you can see that this paper is just published in 2021, which is very, very new. And also in the paper which we talked about for counterexamples to conjectures of gross Matthew and Tuck, you can check in there that these are there. You can check how to go about proving when n is odd that you have the polynomial partial dual orientable genus polynomial is a constant. Now, with the concepts which Prof. Moffat introduced, and with what here we are just saying, okay, let us develop the concepts by doing some simple problems. You start solving what the genus is, then you are able to find the partial dual of your graph, G, delete E, you practice on all those things. Then we have shown you that, okay, there are established problems. People have stated they are doing problems in this field. And I've just put a few problems which people have done with the footnote. But on your own, what can you do? There are research problems which one can do. For example, determine the partial dual orientable Euler genus polynomials for interesting families of ribbon graphs. This research problem, you see, all you need to know is what ribbon graphs are, what are families of ribbon graphs. Can you define, maybe you can define your own family of ribbon graphs and start calculating the polynomials. Start calculating the polynomials. And a second question, which one can consider? Can you characterize which polynomials can arise as partial dual orientable or Euler genus polynomials? Well, just restricting with some other parameters. So characterize which polynomials can arise as partial dual polynomials, partial dual orientable polynomials or Euler genus. Can you characterize which polynomials? So here you need to know other polynomials of ribbon graphs. Then from there, you start working from there with restricting your polynomials to other parameters. So these are just open questions which one can consider. Another thing, can you characterize the ribbon graphs that have interpolating polynomials? I showed you in the previous question what an interpolating polynomial is. Can you find, just characterize what type of ribbon graphs? So these are just open questions which one can think about. Can you characterize what type of ribbon graphs? Another example is, can you characterize ribbon graphs with low width polynomials? So you can ask a lot of questions. You can ask a lot of questions once you understand what is happening in the field. Then you should be able to ask questions on this ribbon graphs, and even on the these polynomials. And here we've only introduced one type of problems for ribbon graphs, like for the research problems. But this is not the only direction which one can go. There are a lot of directions which one can go in topological graph theory. But this is just one area which we thought, okay, let us introduce these open problems. So because it's easy from calculating the genus, then you can calculate the Euler characteristic, you can calculate the number of components, and immediately you should be able to do these kind of problems. They are accessible for people who have just started in the field. They can try to do this kind of problems. And also, these questions which I've put here, you can ask analogous questions for twisted duals rather than for partial duals. So, or for delta matrices and their twist. Some results are known, but the subject has only just begun, so much remains unknown. As you see that the papers, even the paper which they published, the polynomials which we are talking about, is 2020. So there's a lot of work which one can do, and you can just have a lot of, you can have a lot of open problems, a lot of questions which you can try to do. So here, I didn't solve any problem. I'm just introducing the problem because that was the idea, that we just give you an insight of what one can do. So that you can start looking at the area that it is doable. So we only gave you a little background. We didn't assume anything. We gave you very little that you know graph theory. Then from there, if you can use the lecture which Prof. Moffat gave, developing the concepts, then once you have developed the concepts, then you can do you can do those simple problems which we've defined, so that just to make sure that you understand what is happening. And there is also a book by Prof. Moffat, which one can look at. It introduces the concepts very well. It is called Graphs on Surfaces, Dualities, Polynomials, and Nodes. One can also go in there and you'll find that some of the questions which we've asked, you can even find more questions and more examples in that book. And after you have developed those concepts, then you can look at these research problems, or even define your own research problems. Define your own research problems in this field. But these are questions which we put here as research problems. They are new and they're accessible. And this area, this direction of ribbon graphs, it is just very rich for research. And it is accessible to anyone who is interested in topological graph theory. And with this, I will say thank you for your attention. And yes, Prof. Moffat and me will be able to maybe take a few questions, but you can also email us. The email address was given, Prof. Moffat or mine. You can email your questions. Thank you very much.
Thank you so much, Professor. That was a nice introductory to these difficult questions that we need to solve. I saw that there were a couple of questions in the chat. I'm not sure whether you saw that. There were some questions in the chat. Some were addressed.
Okay. Let me see. Thanks. Okay, here I see a question. One person asked, how does the partial dual orientable genus polynomial that is interpolating non-zero coefficients relate to a chromatic polynomial with non-zero coefficients, given that there is a relationship between graph theory and matroids? Okay, so we can't say this is what we were saying about the problem which you were saying, can you find other polynomials which you can relate with the partial dual orientable genus polynomial? And also the other thing here, which one should know, is that with the genus polynomial, with non-zero or etc., already you see that there is a difference with the chromatic polynomial. Remember, the chromatic polynomial, it is unimodal, it is alternating, and also the first coefficient, we know what the first coefficient is 1, etc. So such kind of things. And we know that what the highest power or the order of the polynomial, we know. So it might be a little, it might need some working for you to be able to relate the two. But maybe it's doable, I don't know. I haven't looked at that. Unless, yeah, maybe Prof. Moffat can say something, but I haven't looked at that. Prof. Moffat, is there a relationship which you know?
No.
Okay.
That'd be interesting if there was one. So maybe that should be a challenge to find one.
Yeah, but I'm just also looking at the way the coefficients and knowing the chromatic polynomial. Yeah, maybe, I don't know.
So there are conjectures about things like whether the coefficients are unimodal and log concave.
Yeah.
So Gross, Tucker, and Masur conjectured this. And I believe they're still open and probably very hard.
Yeah.
It'd be really interesting to have answers for these.
Okay. Yeah. So yeah, maybe there is a relationship. Okay, I'll go to the other question, which someone asked. Ribbon graphs are similar to the wheel graphs. Any similar properties thereof? I don't understand. Ribbon graphs are similar to wheel graphs. Similar to the wheel graphs. Any similar properties thereof? I don't know what the person is asking. Are there similar properties, any similar properties of wheel graphs and ribbon graphs? Can the person just write? I don't. Ian, do you understand this question?
So I think this was referring to the picture in the slides with the chords diagrams.
Oh, but okay.
A couple.
Yeah, this one.
Yeah, so these this family here.
Yeah.
Yeah, so it's about interpreting this. So because I just pulled this from a reference quickly, so it's maybe not the easiest thing to interpret. But the idea here is that these are one vertex ribbon graphs, and the red circle is the boundary of the vertex. So think of that red circle as sort of defining where the vertex is. And these blue lines indicate how the edges would be going round. So kind of you've got a one vertex ribbon graph on some number of edges, and all of those edges are interlaced with each other. So I think the question was about just interpreting these figures.
Okay, all right.
So yeah, so sort of as an aside, so this is really representing ribbon graphs as chord diagrams, and there's quite a nice relation between ribbon graphs and circle graphs, which are the intersection graphs of chord diagrams. And on the last slide, there was a word delta matroids, and this direction opens a whole avenue of a whole new avenue of sort of delta matroid theory and analogs for analogs of matroids for ribbon graphs. But that's a whole other story.
Okay, yes. So, and here we have another question. Prof, how can I relate partial dual and chromatic polynomials be related to semi-group theory? How can we relate them to semi-group theory? I have no idea on the semi-group theory. How you can relate that?
Yeah, that I don't know.
Yeah,
I'd be very
no. Yeah. We've already talked about the chromatic polynomials and the partial, but relating it to the same group theory, I don't know. We need maybe to find out how one can do that, because I can't jump into something I don't know.
Yeah, that would be an interesting direction, but I can't immediately see how to get started on it. Yeah, good questions.
Yeah, I think I don't know. I think I've gone through, because the other person wanted to ask about the unimodal, and you already answered. Ian already, Professor Moffat already answered. Yeah.